anisotropic medium, like you change the permittivity for anisotropic, you still have elliptical dispersion. So you change from elliptical dispersion like anisotropic medium. But if you change the epsilon for a negative value and you sort of first for like an epsilon from positive to negative, and what's going to happen in this transitional point with what you say. And the other is if you change from elliptical dispersion to hyperbolic dispersion medium, what's happening in this interface, and then when you put all these circles in it. Yeah.
Excellent. Thank you very much for the question, Margot. First of all, one thing I want to clarify, thank you for asking the question. Everything I talk about today, I was mentioning about changing the permittivity always from positive value to positive value, yes, and both values larger than 1. And the resonance of the medium should be very far away from the frequency of operation. So essentially, it's almost dispersionless. That's what I mentioned at the beginning. Okay. So everything that I talk about today, permittivity is always greater than 1 or 1 for the vacuum, and the changes happens between 2 positive numbers greater than 1. However, coming to answer your question, what would happen if you like to change the permittivity from a positive value to a negative value, or to a value less than 1? In that case, you have to take into account the dispersion. You cannot have permittivity negative without the dispersion. We have done work before, by the way, which I presented before in conferences, in which we changed the permittivity from positive to negative, but you cannot do that for the passive medium. Because for the passive medium, the dispersion requires that when you have a permittivity being negative, that permittivity has to be a function of frequency. So if you have a so-called, standard passive medium, you cannot do that and keep the negative value at the negative. You can do that in the context of the non-Foster circuits, meaning, for example, in the circuit community, there's a phenomenon called non-Foster circuit. Non-Foster circuit, for example, like negative capacitors. Negative capacitors, you can do that, but you have to have a gain medium. In other words, you have to connect it with the transistors and so on to create the gain medium. And even that, by the way, the negative C is not negative for all ranges of frequency because the system becomes unstable. So if you want to change your permittivity from positive to negative, you have to make sure that, first of all, if it's a regular passive medium, that doesn't happen. That cannot happen. You can prove it. But if you want to force it to be negative, you have to create a non-Foster structure. And that means you have to create a gain medium and gain structure and so on and so forth. So you cannot go from elliptical to a hyperbolic structure because hyperbolic structure requires permittivity being negative.
Yeah.
Again, okay, if you want to do that, you have to create a gain medium, you have to create a non-Foster scenario. Ordinary material cannot have that.
Okay, thank you.
Sure.
Hello, can I ask a question?
Yes, please.
Hello, this is Álvaro Sánchez from Barcelona. Hello, how are you? Yeah, very nice talk, full of motivating ideas. I am particularly interested on the last part when talking about the diffusion. Okay. Because, well, of course, I mean, controlling with time electromagnetic waves is very interesting, of course, but electromagnetic waves have intrinsically time, right? But diffusion is like something different. I mean, because it looks like because of entropy, it looks like everything should be more fixed, right? I mean, the time dependence. So I think playing with that is particularly interesting. So I found your work very, very interesting, actually. So my question was, you have been applying these ideas to the electric case because you can control the capacitance and so on. Sure. And you mentioned also that this can be applied in other physical fields. For example, in thermal, maybe it would be a little difficult to implement because you would need some pumps or something, right? Yes.
That's right.
And you also briefly mentioned, very interesting, I mean, the thing with acoustic in graphene and so on. But I wonder, and I would like to know your opinion about, I think that there is another field in which these ideas can be very relevant, which is for controlling static or quasi-static magnetic fields.
Yes.
Because I think in that case, you could have a very good control of the local permeability of the material just by applying, for example, local magnetic field or local currents and taking advantage of the natural non-linearity that you have for the ferromagnetic materials. So I have like a double question. Do you think these ideas are interesting? Because I really think this could be implemented in practice in the field of magnetism, which so applications that I think in technology. And the second, if also related to that, if non-linearity in general can also help you strengthen some of these effects that you nicely discussed.
Oliver, thank you so much for your questions, both of the questions. And I know, by the way, you have a great interest in magnetism. So that's a very interesting question you mentioned. Let me start with the question with regard to magnetism aspect of this. And as you said, that's a very good point. If you can control permeability, particularly with respect to the, kind of like a static scenario and so on, by an external field, yes, I mean, that would be quite interesting to consider. In that sense, instead of epsilon, you're changing mu, for example, obviously, and you can do that. So I think that's an interesting point you raise, and just thinking about it, right now, I think that could be possible in that regard, that you can change that. So with regard to a nonlinearity aspect of that, so one thing, by the way, you need to consider is that in principle, all of these temporal metamaterial, temporal variation of that involves another energy other than electromagnetic energy, because you make changes in the medium, so to speak. So in that sense, fundamentally, that's very different than, let's say, the standard spatial inhomogeneity. For example, in the first few slides, when I showed that you have a wave, and then you change the temporal, you change the permittivity temporally, and you get a backward wave and forward wave coefficients. If you look at those coefficients and you square each one of them and you add them together, you not necessarily get one, because part of the energy is also the energy that the material has to spend in order to make that change. We don't have that issue in the regular Fresnel scenario, because if you have just sitting medium there and you send the incident wave, the transmitted wave and reflected wave, when you add their energy together, is the same as incident wave. So that makes the problem more involved from the point of view of energy consideration. Nonlinearity. Now, nonlinearity is quite fascinating, because nonlinearity can be used in order to make these changes, for example. In fact, we have a project on that to see how we can actually have, let's say, a pump signal will come, hit a layer, let's say a surface or something, changes the permittivity of the medium as a function of time due to the temporal variation of the pump. And then on top of that, you would have a probe signal that's going through. So if you are referring to the nonlinearity in that sense, that can actually add to this system as well. Well, now that you mentioned, Oliver, with regard to nonlinearity, let me add some comments in general over here. One might say that, okay, essentially, when you're changing the permittivity of the medium and you're changing the frequency, it's kind of like a nonlinear phenomena, because the frequency is changing. But bear in mind that this phenomena, by changing the permittivity, the system is not nonlinear from the point of view of intensity of your field. In other words, your frequency would change from omega-1 to omega-2 regardless of what's the amplitude of your electromagnetic wave. This change of the frequency is because, of course, permittivity is changing. Now, if we add also nonlinearity because of the effect of the amplitude and intensity, that makes the problem even more with high degrees of freedom that you have there. So I would like to point out this issue that so far, all these things that I talk about, the problem is independent of the intensity of the electric field there. So in that sense, epsilon is not nonlinear in that sense. But again, frequency is changing. So the mechanism has some aspect of this changing of the frequency.
Thank you very much. Thanks.
Excellent. Do we have any other questions from the participants? I'm sure we do, actually. Don't be shy.
Hello?
Yep.
Yes. Hi, Nader. Yeah. So
how are you?
Yeah, I'm fine. Thank you. Yeah.
Nice to see you.
So, nice to see you here. Yes. It's a fantastic talk. Thank you very much. And just have one question regarding the temporal length. When you mentioned, the wave can be backscattered, to focus the point again.
Mm-hmm.
And I just wonder, what's the criteria for the period of the temporary change of the permittivity? How is it related to the frequency of the light?
Oh, I see. So, Sean, are you referring to? Let me make sure I understand your question. So you're saying the relation between
the relation between? Yeah, I remember. Your permittivity is changed in a periodic manner, right?
Yes, that's right.
Yeah.
I mean, so you're talking about. Let me share my screen.
Thank you. Yeah.
Let me share my screen to make sure I answer it correctly. 1 second. Let me see. Oops. Okay. Can you see it, Sean?
Yes, I can see that. And
let me show you this one. This one is interesting.
Yeah, this one,
now,
right.
In this case, we have a, slab. So this thickness in space is fixed all the way. And let's say the incident wave is coming obliquely. Take a look at. I'm going to take a look at what happens in the backward wave. So the wave is. So this is a forward wave. This is a backward wave. You notice the backward wave is going to stop at some point if you don't repeat it. So if you just have one, the wave. Let me look at this. Of course, these are all connected to each other. But let me take a look at it. This one is coming. See, this is coming. This is coming over here. And if you don't repeat it, it's going to stop here. So in order to make sure that the backward wave continues, you have to keep changing this. The question is then what should be that temporal, what should be that delta t in order to change that? The answer actually comes right from here, this expression. You notice depends on the thickness of this and depends on the angle that you're coming over here. So if we know the angle and we know the thickness, you can work it backward to find out what should be this spike in order to make sure that the backward wave is stitched together over here.
Okay, yeah, I got you. So basically, there's no direct relation between frequency and.
Oh yeah, you're talking. I'm sorry, I misunderstood you. You're talking about the frequency of the wave.
Yes.
Yes. So yes and no. On the one hand, you can see that it's not there. Now, this t may not have directly relation to that. However, this rapid variation that you have over here, you would like this to be done in the delta t smaller than the period of your wave.
Okay.
So I'm talking about two time over here. One is the time between the two consecutive pulses. That depends on this thickness and the angle. But then there is also a time when the epsilon stay at epsilon 1 and come back. This is a much shorter time. That time should be less than the period of your signal.
Okay.
And of course, by the way, nothing is happening instantaneously, obviously. So you have to make sure the rise time is much faster than the period of your signal.
Period. Okay.
Yeah. And by the way, that's one of the reasons that when we went to this one, you notice, that's one of the reasons when we went to this one and we start with this line source over here, you notice in the middle, we have a thicker region than on the side. It's because this wave that's coming over here is going to go through this path, whereas this one is going to go through this path. So we wanted to make sure that the backward wave would stitch together over here. So that's what this is not just a regular rectangular slab. It has a little bit of variation
here. Yeah.
Okay.
Yeah. Thank you very much, Nader. Yeah.
Sure.
Thank you.
Thank you.
Sebastian, can I ask a question?
Sure.
Thank you, Professor, for this great talk. So, I have two questions. So, the first one is related to recent work by Professor Pendry, where he has shown when the ratio between the time modulation and space modulation is equal to the speed of light, you would have kind of luminal metamaterial and amplification due to the compression of line of force. So in your problem of diffusion, is there like kind of speed or speed of effective speed when the ratio is equal to this speed, you would have like a kind of amplification?
Thank you for the question, by the way. Of course, in the case of diffusion, as you know, we don't have velocity there. I mean, in that concept, it's very different than wave, of course. We don't have the velocity, so that issue is not here. However, your question can actually point to very interesting phenomena. Is that you notice, by the way, when I was mentioning it about the spatiotemporal modulation, and I say capital omega and k that I put over there, you notice that when we did the homogenization, the capital omega disappeared there. The reason for that is because we assume our capital omega is high enough that the period of modulation is smaller than the diffusion time, so to speak. So in other words, we assume the diffusion phenomena is a slower phenomena compared to the period of your modulation. However, if the period of modulation become comparable with the temporal, time constant of the diffusion, something interesting may happen. We haven't looked at that yet. We don't know. But that's an interesting question. We don't know that. But again, because diffusion doesn't have a velocity like a wave has, it's a completely different phenomena. But your question is an interesting one in a sense that what would happen if you make for example, think about it. If the modulation becomes so slow, so then in that case, diffusion may happen before the next cycle of modulation comes. In that case, we don't see any effect. Or if the modulation becomes very fast, as we have done over here, then of course the diffusion will have an effective diffusion, so to speak, and that works. But if it's something happen in between, do we have an interesting phenomena? I don't know. That's a very good question, and we'll look into that.
Okay. And I have another question, like regarding this graphene, because like in 2013 we had a work where we have shown that by inducing a flexural wave on graphene, we can excite surface plasmon.
Okay.
So do you think this can be applied with this?
Oh, okay. I would love to see that. I didn't know that. If you can send me, your paper on that, I would love to read it and we can talk about it. That would be very interesting. Yeah, we were just thinking, something in the future that we may want to consider. But if this has been already an interesting possibility, I would love to look at that. Sure.
Okay. Thank you.
Nader, sorry. To come back on this idea of diffusion equation, if you put for the diffusion profile that will change both in space and time, the inverse of the diffusion law somewhere, can you not match diffusion and stop the diffusion?
Matthias,
because the other idea for waves was to send a wave and to make a modulation, a spatiotemporal modulation, which is also with the same behavior than this wave. When the two interact together, you can amplify or you can do funny things. Now, imagine that you have a diffusion profile that is created by a classical diffusion coefficient. And now you modulated the diffusion profile. Is it possible to modulate with an inverse law?
I see what you mean. Thank you very much, Matthias, for the question. If I understand it correctly, let me repeat that just to make sure I understand it. So you're saying in a standard diffusion that we have this thing coming down, okay, something happens. Now, can we actually change the platform in space and time such that the diffusion kind of like a time reversal, what you're talking about?
Exactly. It will be very funny because diffusion equation is not a time reverse invariant.
No, it's not.
Reversible equation, but if you make a diffusion equation with a diffusion coefficient which vary both in space and time, can you find some law which can give you the impression that it is no more irreversible?
That's interesting. So the short answer is I don't know the answer to that question, but let me just bring my slide. Let's think about it together to see. Let me share my slide. 1 second. This is a very interesting point that you raised. 1 second. I share. Okay. Let's see. So let me go to this slide. Let me go to the end of it, because that may have some answer to your question. 1 second. So for example, Matthias, let's take a look at this one. This, of course, is the analytical results that we are plotting over here. And you notice either the diffusion goes in this direction or the diffusion goes in this direction. Okay, that's fine. But when we actually look at this, now this one, so you notice here in this theory and experiments that we did over here, you notice we put a voltage source to this end of it, and you notice how the charge actually accumulated over here, and it actually builds up the charge over here. Now, okay, so one might say that, okay, rather than this being diffused uniformly over here, it's actually build up at the other end. Now, this is the opposite of that. In other words, rather than building up over here, it's basically, in a sense, the charge doesn't diffuse along the structure and stops over here. But let me show you the next slide that I showed. Here, it's interesting. By the way, this is just a simulation. This is not an experiment. So you notice what in this simulation, what we did is that part of the region, we put a phase different than the other part of the region. So as a result, the charge that's coming from this source and this source actually accumulates in the middle. Now, does it mean that this is what you're referring to? In other words, kind of like, you know, it building back. I don't know. I mean, the system is showing this, by the way. But of course, this system is an active system. In other words, you have to put energy into the system.
It is not a passive system.
Exactly. Exactly. It's not a passive system because this system has to work in order to force the charge to go opposite to the direction of the natural equilibrium diffusion. So, by the way, of course, this is the opposite of that. In other words, this gets it to the two ends rather than in the middle. So that's an interesting question. Let's talk about it. We can talk about it offline. I'm interested to see.
Okay.
Comment, is it possible to use a negative element with a negative conductivity, negative conductance?
Yes, in that case, you have to have a non-Foster circuit. Yeah, you have to have a non-Foster circuit in order to do that. Here it's just essentially is by this putting the energy into this spatiotemporal modulator that we have over there to do that. But this is a very interesting question, and I would love to talk to you offline to see how, first of all, I want to make sure I understand your question carefully. And second thing, if this spatial modulation can actually provide an interesting non-equilibrium system for you.
Thanks.
So let's talk offline. That would be interesting to see how it can be.
Excellent. We initiate some scientific collaboration. Wonderful. Any more questions? Please come forward with your question. It can be also a naive question. Don't be shy. No more questions?
I'd be happy to answer any question if any come up on that later on. Just please send me an email and I'd be happy to answer.
Yeah, so we shall thank our speaker again for this wonderful talk. And please do not hesitate to contact Nader by email or any other mean. And next week, we shall have a webinar by Vincent Tournat from Le Lomme. So it's the University of Le Mans in France, and he will talk about nonlinear metamaterials and the like. Thank you very much, Professor Engheta. This was really, really an inspiring talk.
Thank you very much, Sebastian, Muammer, and Bogdan, and thanks all of you for attending the talk. Thank you.
And please, everyone, stay safe.
Thank you. You too. Bye-bye.
Okay, thank you. Bye.
Bye.
Thank you.
Wonderful.
Thank you very much.